Dear students, we have already seen the problem which can be solved using greedy method. So in the greedy method, we used to solve the problem with the help of ratio method, where we have the number of items. We'll calculate a partial value or a 1 unit value for that particular item, and we'll arrange all the ratios in the descending order, and then pick the first, the local best, and then we add it into the knapsack. But there are situations where this greedy problem solving method is not applicable because the items are solid, which cannot be broken into parts, so that we will not be able to calculate the partial or per unit value of that particular item. Since we will go for a new problem solving method, that is dynamic problem solving method. We have also solved a knapsack problem using greedy method, but in a greedy method we will having the material in the form of ash or chemical, so which can be partially divided, whereas the partial part of that can be calculated with the respective value, partial value of that particular item. So this kind of, for solving these kind of problems, we will have to generate a ratio for that particular partial item and then sort it into a descending order, find out the best. This is what we do in a greedy method. But whereas in some cases we do not have the elements, the material, which can be cut or divided in some parts. So for example, if we have the materials as shown here in the example, that a material A, B and C, these are solid material like a metal or a brick, which we cannot cut in the parts. Either we take item completely or nothing. This is what we do. If item A is having a weight 10, the value of that item is 100. Item B with weight is 40 and the price of this 40 is 280. Whereas item 3, the weight is 20 and the value is 120. We have a knapsack with the weight 60. So we will fill the knapsack with these particular items. So either we take a complete item A with the weight 10, put it in the knapsack. If we are not like to have this item into the knapsack, we'll directly reject it. So that is why we say we have only two options, either take it completely or leave it. That is why we say this as a 0-1 knapsack. The possibilities are only two, either take or leave. So this is what the problem will try to solve. So for solving this problem, what we do, we will try to enter all the items into the knapsack. The knapsack size is 60. We cannot take all three items because it will exceed the limit of 60 weight of this particular knapsack. So what can we do? We can do is we will add the item A and B. The weight of item A is 10, weight of item B is 40. So 40 plus 10, 50. Since the weight of knapsack is 60, 50 is almost comfortable in the knapsack. But if we put this particular 50 item into the knapsack, then the profit that we can generate from taking item A with the weight 10 is 100. Item B with the weight 40 is 280. The total profit we can earn is 380 for a 50 weight. We cannot take item 30 because it will exceed. So maximum profit we can get is 380 if we take item A and item B. So let's check almost all the possibilities, because number of possibilities are considered for finding out the best output. We just saw what can be the best profit we can achieve if we include item A and item B. But if we include item B and item C, so 20, 40 for item B, 20 weight for item C, the profit that we can earn is 280 for item B and 120 for item C. So we will get a profit, it's a 400 for a 60. 40 plus 20 is 60 maximum weight. For a maximum weight 60, we will get 400. This is 60 is more comfortable, profit is more compared to the previous version what we have added into the knapsack. So we have one more option that to be calculate item A and plus item C. If we calculate weight for A item is 10, C is 20. So 10 plus 20 is equal to 30. So 30 is more comfortable in the knapsack with the weight maximum capacity is 60. So we can earn 100 for item A and 120 for item C. So total is 220. So 220 is the maximum profit that we can get for a weight 30. So with all these three possibilities, this one will provide the better output for the knapsack. So 400 is the maximum output, weight is 60. So these two can be removed, neglected for finding out this one as a best. So what we have done, we have found all the possibilities which can be generated with the existing items. So this can be converted into a dynamic programming solution. A programming solution is this is a programming function with which we will be able to execute the algorithm. P is the profit, it's known as values, W is the weights, N is the number of items what we have, W is the maximum weight. So that is what we had seen, it's 60. So this dynamic 0-1 knapsack function, we will have a profit value array, the weight array with respect to I. So items I1, I2, so I is equal to 1, 2, 3, 4. N number of items exist, I to N, the values, respective values are 1 to N. So we have seen in the table. So what we do is, we'll create a matrix C that we have seen in the last lecture. We have to generate a matrix with which we will be able to calculate the maximum profit, and in addition to that we will be able to memorize the perfect solution for the problem. So this for loop will, these two for loops will allocate a matrix C with the empty matrix which will hold 0 on all the places. W is the maximum weight that we would like to go for. So if the weight that we include for first item, see I is going to increase from 1 to N. If we include the weight of item I into the knapsack, if it is smaller than the weight, then only we will calculate the price. Otherwise we will just neglect the item. So profit for that particular item which we have included in the knapsack is entered, the index, the item, and the respective weight is also calculated for calculating the price of that item, and we'll enter it into the matrix for storing the current scenario, current profit that we generate. So this is, if this is better, this is profitable, then we will include it into a matrix. So this C in the bracket IW is equal to PI plus C I minus 1 comma W minus WI is the optical substructure, the solution of this particular problem. So this optical substructure, once we generate while designing the problem, then this particular optical substructure is applicable everywhere throughout the problem statement. If this is true, then we'll proceed. Otherwise, we will have to leave the item and we'll continue with the same what we had calculated for a previous item. This is already shown in the solution that we have generated for a matrix. Same has been done for the rod cut problem. You can refer the same. So this is what the 0-1 knapsack problem is, and this is how we execute it in a programming way. Thank you. That's all for today. So we'll meet in the next lecture. Thank you.